anything that you can do to minimize your cognitive overhead is like extremely important to program correctness and design and optimization. Like if you think about your brain as like having some like limited working memory, you want to use as little as possible in general so that when you need to, you can use the rest of it. So as much as possible, you want to make your programs as simple as possible so that when you need complexity, you can access it.
Hello and welcome to another episode of the Devs Do Something podcast. Today's guest is the man, the myth, the legend, Big Tech Sux, or BTS, as I'll refer to him throughout the rest of this intro. You might know Big Tech Sux from Twitter as one of the largest proponents of and contributors to the Vyper smart contract programming language. BTS has contributed a lot to Vyper's development, and in this episode, we talk through Vyper's history, some of the trade-offs and design decisions of Vyper, and we go really deep on compilers and programming languages more broadly. BTS is someone who's thought pretty deeply about programming language design and how it might look in the future when it comes to Web3. He's thought about how the language landscape is going to look in the next several years when it comes to Web3 development, and he's very focused on making the Vyper developer experience a great one. So we talked through some of his thoughts on how that developer experience is going to improve over time, and we specifically talked through a new piece of software he's worked on called Titanoboa, which is making that developer experience honestly one of the best in all of Web3, in my opinion, after doing research and having this conversation. So if you're Vyper curious or if you're a Vyper maxi, I highly recommend you listen to this episode to just download a wealth of knowledge about programming languages and more about Vyper into your mind. I hope you enjoy. All right, so we are here with the legendary Big Tech Sux. Welcome, man.
Hi.
Sweet. So we're super happy to have you here to talk through all things Vyper and compilers and some other things like that. But before we get into anything super technical, we'd love to understand just from a high level, like, how'd you get into the space and what got you started with Ethereum?
Yeah, that's a really interesting question. I've been like a bit on my background. I've been like a professional programmer for, I think like 10 years now, which is kind of weird to think about. I started out in automated trading, low latency stuff. And, over the years, I've just kind of gotten more and more into programming languages because I think that like the ability to express yourself well through code is like the most leverage any programmer can have. Let's see, I started learning about Ethereum in like 2017 or so, and was working on I had an idea for a decentralized exchange, and I like wanted to implement it in Vyper because, I had some background with programming languages and, I was interested in smart contract languages. And I'd heard that Vyper was like cool. So I like tried implementing some stuff in Vyper. And then I realized that like it like didn't have some features that I wanted. And so I was like, well, it's like a kind of seems like an approachable project. So I like started contributing some features, and then like it all went from there.
Yeah, for sure. You've definitely gone very deep into Vyper, obviously. How has Vyper evolved since you started contributing and playing around? Like, are there any like I would love to hear kind of like your perspective of how far the language has come in the last couple of years.
I'd say Vyper has matured a lot. I guess, of course, I would say that because I've been working on it, but it's gone from, it has areas of the compiler that are like somewhat buggy to like in the last 2 years. I've been working on it full time now for a year. Before that, somebody from Curve was maintaining Vyper, and there's a lot of tricks that we've come up with in the code gen to like do efficient calls and stuff like this. And we've added like tons of stuff to the front end. One important thing was that a couple of years ago, well, several important things. A couple of years ago, Vyper like didn't have a separate type checking pass, And so that like kind of caused a lot of issues in the UX. So like it was kind of hard to catch exceptions and display them properly. And that was moved out into a separate type checking phase. And so now Vyper exceptions are pretty good, I think. And like one thing I'm kind of focused on is like good recommendations. So like when there's some like front end exception, like a user error, we'll try to recommend something reasonable. And some other things, we've gotten to API compatibility with Solidity. So like it used to be that in order to like call certain kinds of interfaces, especially with dynamic arrays or like bytes for things, you had to like construct the call data manually, and like now you don't, which is I think pretty useful. And the code gen, I want to say the code gen is generally more robust and like bug free, which is obviously something that's important to anybody who's using a compiler. Like I've talked to multiple auditors and I'm like, so you guys like talking about their process, right? And they're like, oh yeah, we like read the user code. And I'm like thinking in the back of my head, and then I verbalize this, right? Like, so like, do you worry about compiler bugs? And they're like, no. We just like kind of assume the compiler engineers are really good and like that the compiler is like completely correct. And I'm like, got it, no pressure. Okay.
Yeah, it's a pretty bold assumption. Oh man.
Right.
Yeah.
And like to a large extent, I think both Solidity and Vyper have been pretty good about not producing bugs in production code, to our credit. But you know, it's possible, right? We're human. And then a bunch of developments have happened on the tooling front, which we'll probably go over later in this call, which I'm pretty excited to share about.
So yeah, something that I've kind of heard come up, you know, here and there in conversation about some of these new languages popping up and people, you know, kind of working on these compilers, and kind of this interest in compiler tech, you know, is kind of raising a little bit in the blockchain space. Yeah, so right now, as far as I know, Vyper and Solidity use different intermediate representations altogether. And so there was a little bit of discussion before about like basically creating like a sort of unified, you know, standardized intermediate representation. For people that might not know this, basically just it's a representation between, you know, your code and the actual EVM's code. So, I mean, what do you think about, you know, do you think there's a space for this sort of standardized IR? And I mean, what do you think that looks like, you know, a few years down the line in terms of language development?
Yeah, that's a really interesting and also broad question. So there's several aspects to designing a good general purpose intermediate representation. For one thing, the obvious thing is like, why don't we use LLVM? And there's a few reasons for that. For the most part, LLVM is like bug-free, or, you know, it doesn't have too many bugs, but it like is kind of, I don't want to say anything out of line here, but like it was basically designed for C and C++, whose specs have a lot of undefined behavior in them. I don't want to say that bugs in compiling C code are like less critical than Vyper and Solidity, but like maybe they are.
There's no money at stake. There's no money inherently at stake when you're writing C code, right? Obviously, you want to be secure, but there's no direct honeypot of $10 million sitting there, right? So I get what you mean. I think you're directionally accurate there.
Smart contracts tend to, in by design, are much longer lived than a C program. Like if you find a bug in a C program, like in the compiler, you just recompile it. But on the EVM, it's already deployed. Like, get wrecked. So
yeah, the nature of maintainability is totally different there too, right? Because there's these assumptions that like the smart contract is immutable, right? Unless you have a very like well done upgradable pattern, right? So I totally get what you mean. That makes total sense.
Right. And then the other thing, which is maybe, yeah, I would probably want to say more important, is that LLVM is designed, like its entire architecture is designed for like register machines. Like you can search Google like how to build a stack machine backend for LLVM. Guess what? Probably every smart contract compiler engineer has done. And the answer on Stack Overflow starts with the sentence, "Don't do it." and the reason is like it's just not really the same animal. Like you can kind of get away with it by like simulating registers with stack slots, but it would be hard to get like the same level of performance as like LLVM does for register machines, because just the optimization routines in LLVM are just like designed for register machines. There's like no routines that are named like optimized code for stack machine. So I think that an IR that would work well for blockchains would need to be designed with that in mind. There's also like lots of different, I don't want to say competing interests, but like different interest groups in like, let's call this blockchain IR, right? There's like compiler engineers, which is like me, and like all we care about is like being able to optimize the code and for the compiler passes to be like relatively simple and like easy to implement and easy to audit and so forth. There's also like different blockchains. I mean, in the blockchain space, I think there's like two basic classes of virtual machines. There's like stack VMs. Well, there's people try to do register VMs, but we don't really talk about that. And then there's like ZK VMs, which are like a completely different architecture. Ideally, and I think that this is required in order for ZK VMs to really take off, compilers and, blockchain IR infrastructure has to be able to target both of those. There's also security people or auditors. And then there's also like tool writers, like people like Truffle or people who are writing debuggers. And all of these groups have, basically the same goals of like, improving the ecosystem, but they all have different desires. And so this blockchain IR has to like be able to have enough functionality to be able to cater to all these different groups.
Yeah, that's really interesting. I hadn't even thought about the fact that you would really need a good, IR for ZK VMs. I mean, the experience that I've had with it so far, a lot of the ZK languages are very, very low level, right? Like they're very close to, the actual like, I mean, some of them, I guess you could call them opcodes sort of, right? But like they're very, very close to that. And like, I think the biggest leap that I've seen from it so far would be like Aztec. But even then, like it is still like very, very close to that low level stuff. I think if somebody could actually build an IR that could target, like the EVM and then like ZK VMs and maybe even non-EVM chains, I mean, that could be, that seems like a holy grail of compiler tech, right? But yeah, a lot easier said than done, I imagine.
What's the potential for an IR like this? Like, is it strictly something that would have to be EVM based and maybe ZK EVM based, or could you do something where it's like you're using this within the Cosmos ecosystem or within the Solana ecosystem as well? Would there be any kind of landmines to avoid when branching out to non-EVM?
I don't think that there would be too many problems with that. I think that if it were sufficiently high level to target EVM and also ZK VMs, you could also target something like Solana. I mean, it would be really kind of strange because you would be like generating Rust code, I guess. But I think that would be relatively straightforward to implement, because basically the level of abstraction that you would need in order to target a stack machine or a ZK VM would be sufficient to also be able to target something like a Rust SDK. I mean, so the level of abstraction that you need is you need to distinguish between computational operations like loading and storing from memory, math, stuff like this. And then you can think of them as syscalls, so like interacting with the blockchain state. So these include, S stores, S loads, calls to external contracts, getting blockchain environment stuff like block number or whatever. And a good IR design would distinguish between these kinds of things sufficiently so that you would be able to like compile them these syscall things into API calls in the appropriate SDK and compile the rest to like the computational side of the VM.
Yeah, I mean, I think obviously it would have to be done at the back end, and there would have to be custom implementations maybe for each environment. But it's interesting to hear that that is a theoretical possibility, and maybe on a long-term timeline, someone builds something like that. So we'll see. On the level of languages, though, right? Bringing it back to like Vyper and things, we can get into some of your developments with Vyper and some of the future roadmap with Vyper. We're going to talk about some of the really awesome things you're working on with, I think, Titanoboa, right? Is that how you pronounce it?
That's my reading of it.
Okay, cool. Yeah, we'll definitely talk about Titanoboa in a bit. But what are your thoughts on how languages play out within the EVM? Do you think this is going to evolve into like one language mostly winning? Do you think it's going to be like multilingual? Do you think someone will come out with a new language and compiler at some point in the next 5-10 years? Like, how do you think this plays out?
I think that the space for languages will continue to be competitive. I think that people are going to continue to like build new languages and that make it more convenient or easier to write safe smart contracts, or that have better optimization properties. Well, I'm a Vyper maxi, which I suppose one should hope I am. What I've learned since working on Vyper, not just as a maintainer, but also as somebody who wants Vyper to be adopted and who's really interested in having more and more people use it, I've learned that it's not so easy to change languages and environments. And this is something that I guess you can realize by like some introspection too, right? Like it's hard to switch between different languages. And people are always saying like, yeah, you should use the best language for the job. But like, how are you going to deal with like this 10,000 lines of code that you have written in another language? And even when there's bindings between languages, it's like not super simple. Even between languages that are, in the same family and fairly similar. So like I was talking to somebody who manages a team that works on a very large C++ code base. And I was like, why don't you guys like migrate to Rust? I thought like Rust is the cool new thing. And they were like, well, there's a few reasons. One, the Rust performance isn't as good. And in the case that like 5% of your performance profile really matters, then like the quality of the compiler really matters. I mean, maybe that's something that, changes over time, the LLVM infrastructure gets better, it, is competitive or better than GCC. The other thing is I was like, okay, but like, right. So suppose that the performance were the same. They're like, well, still we have like, I don't know, hundreds of thousands or millions of lines of C++, and like we have all of this build infrastructure and like people are used to writing C++, and even if we were to wrap them in libraries, like you'd have parts of your code base in Rust and parts of your code base in C++. So if you're trying to migrate it over time, then you like introduce this cognitive overhead of like switching between the two languages. And like I know that a competent developer can like pick up a new language, but like it's overhead, it takes experience to like know a language really well, and switching, like it just kind of introduces a lot of, I would say overhead is the right word for this. So, I mean, if you're compared to general purpose programming, like if you go to Stack Overflow or something and they have their developer surveys every year, and there's like language diversity in the Stack Overflow survey, right? Like people are using Rust, people are using C++, people are using Python, people are using JavaScript. But if you think about it, there's really like one language per domain. Like people are using JavaScript for web development, obviously, and there's like some backend stuff written in JavaScript. And then like for performance sensitive code, obviously you need to be writing something lower level. For data scientists, like people are usually reaching for R or Python. And so I think that the domain of smart contract programming is small enough that it may be kind of multilingual, but I think that most people are going to gravitate to one or two languages.
Mm-hmm. Yeah, that makes sense. That makes sense. On Vyper specifically, I mean, for you, this is going to be a simplistic question, but I think it's good for our listeners just to have this background before we go deep into some of the new developments. What specific design choices, outside of it being Pythonic, right? That's visible like the second you get to the docs, you see a single contract written in Vyper. What are some of the more explicit design decisions that yourself and the Vyper and people that have also worked on Vyper in the past have made?
I think that the decision to be Pythonic, in appearance, actually semantically, it's very different from Python. But to be Pythonic has driven a lot of our decisions around the UX. So we'll pretty much reject any language proposals that are not compatible with Python syntax, with the Python AST, and except in very rare cases. So like there's a couple keywords like struct, implements. Sorry, actually implements is syntactically Python, but like struct, interface are not Python keywords. Log is not a Python keyword, but we're able to transform them to Python syntax with a very simple pass. Vyper is also meant to be very analyzable and semantically strict. You know, it's statically and strongly typed. And it has restrictions on gas usage. So like everything has to be bounded. All memory allocations, which are, by the way, behind the scenes, but all data types are bounded in size. And basically, you can calculate the upper bound for the usage of any Vyper program, the gas usage or the computation usage. Recursion is not allowed. Which, by the way, people, I think that the restriction on loops is like maybe excessive, but like people see that like Vyper doesn't have recursion, and they're like, doesn't that mean like it's like not Turing complete, or it's like not as useful as languages that have recursion? And I've like actually never seen any smart contract that uses recursion or mutual recursion on purpose, like ever. Like you might have like an external callback into the same contract, but you can do that in Vyper. Also, Vyper has no, I think this might be well known, but Vyper has no inline assembly. So you can't drop down to EVM level. That is a little bit annoying sometimes, but I asked people about this, and usually there's two reasons people want to drop down into assembly. One is they want to use an opcode or an EVM feature that we don't expose, which is like, okay, we should implement that. And then the other is like, somebody was like, well, whenever I write a branch, like an if statement, I always like prepend the condition with is 0. And it's like, well, the optimizer does that in Vyper. Like, and I've talked with other compiler teams, and they're like, yeah, exposing assembly is like makes a lot of optimization and semantic analysis like really hard. So those are the three main things. So Pythonic syntax, everything is bounded, and no inline assembly.
You know, on the inline assembly, because it is a bit of a hot topic sometimes. Basically, do you think that like inline assembly is something that is going to be basically required by any smart contract language out there, or do you think it is more or less a failure of the compiler? Because like you said, sometimes it's to expose features that maybe the compiler doesn't expose, or it's for some sort of optimization, right? And so, I mean, in terms of optimization, right, like we ideally a language would be able to, or a compiler would be able to handle that under the hood. But in terms of like built-ins, like Vyper has built-ins like EC, like elliptic curve math. You have things like unchecked arithmetic, since everything is checked by default, right? So like, any features that don't exist, let's say in Vyper now, like ideally they could just be, in their own function. And then where's the need for inline assembly, right?
So there's a couple, that's like a very interesting question. And I don't think it's really possible to answer it from a theoretical level. Like, yes, obviously it's very useful sometimes to be able to like get around whatever the compiler is trying to keep you from doing. But as I said, that allowing assembly introduces issues for the compiler. It also introduces issues for auditing. I think it takes longer to audit like code with assembly in it. But I think that we can find the answer kind of in the history books. So like if you look at C, like 30 years ago, people were writing inline assembly all the time. And over the years, the optimizer has gotten better. GCC and LLVM expose more built-ins. The standard library is better, so that like anybody learning a systems language today will probably actually not be exposed to assembly. And so I think that over time we'll see less and less need for it as compilers get better and the appropriate built-ins get exposed to the users. We've talked internally a lot about like whether, especially for library writers, who are like trying to implement new data types or trying to do like right now, the only way to expose something that is not in the language already is like for the compiler to implement it. So like it might give a way for the compiler not to have to implement so much stuff. So like as far as a decision for today, it might be very practical to expose assembly in one form or another. But also with the caveat that it's a lot easier to put stuff in than it is to remove it. So for the time being, we don't have any plans to add inline assembly to Vyper.
Yeah, there are trade-offs for sure to decisions like that. Another one, just by nature of being Pythonic, is that Vyper has no inheritance, right? So something that Solidity devs are very used to is yarn add or npm install open Zeppelin to my folder, and I start using those contracts throughout my project. How does losing inheritance impact code reusability within the Vyper ecosystem, and how much does that actually matter in your opinion?
Python does have inheritance, so it's kind of a break from Python that Vyper doesn't have inheritance. Inheritance in Python is super useful because of the way that Python programs are often written. There's often a lot of monkey patching. You can override a single function in an object. But Vyper doesn't have inheritance because, well, early on, somebody decided that it was not good for the language. I think in a lot of ways it's true. The smart contract programming model is different from the object-oriented programming model. I don't want to conflate inheritance with code reuse because there's like a lot of ways of having code reuse without inheritance, even since the time of C. You can like use C headers and call like C libraries, and C doesn't have inheritance. OCaml has a module system, which is like, I'll ask OCaml programmers. So OCaml has two kind of module systems, which is kind of interesting. One is the original module system, and then the other is the object-oriented system. And if you ask OCaml programmers when to use objects, they're like, I don't use them. So OCaml just has this module system, and it's a very interesting and very well-designed system, but it has some complication for the users. It's basically a little bit complicated to use. So I want to clarify that inheritance does not equal code reuse. Code reuse is super important. You can't design or build large systems without code reuse. It's hard to prevent bugs without code reuse. If you reuse code, you get more miles on like reused functions. I don't know if it's possible to stress how important it is. Being able to reuse code is something that is very important for Vyper's future. And I'm actually working on a library and module system for Vyper right now. One reason we haven't had it so far, besides it wasn't in the beginning, is that we kind of want to get it right. We want it to be easy to reason about. Maybe I should talk a little bit about why smart contract programming is very interesting. So object-oriented programming, which is kind of where Solidity gets its inheritance system, it was a really important step forward because one thing it does is it's kind of a blessing and a curse. It conflates functionality with data locality. So like an object is like some set of datums, that are all close to each other in memory. And it's also got a bunch of methods on it, right? So if you want to call like dog.speak or whatever, or like dog.do something, in the implementation of that method, most of what you need is already there. And it encourages this like kind of encapsulation property. So like dog.do something, you can access all the properties of the dog, and it's like going to be local kind of to the code where it's implemented. You don't have to like go somewhere else to find out where like the dog's age is or the dog's height, So it has really nice, that kind of gives you really nice encapsulation properties. If you move to smart contract programming, smart contracts are kind of like objects with some very important differences. Contracts have persistent storage, which is kind of really interesting. If you're like redesigning the EVM from scratch or smart contracts from scratch, you might expose storage as like a file system or like a database, which it's kind of like a very simple database. But you might use like some kind of file system API, like open some area of storage, read and write from that area of storage. And what smart contract language designers did from very early on is actually expose storage more like you would see it in object-oriented programming. So like properties on the object are actually living in storage, even though like in traditional object-oriented programming, an object is like something in memory. And so this has really interesting ramifications, like the layout of a smart contract. So like the behavior of a smart contract is like really tied to its storage layout. And like anybody who's tried to upgrade a contract can tell you that this like makes it really complicated. There's also some name spacing issues with inheritance. Let's say A inherits from B, and like, I don't think you can do this in Solidity anymore, but like at one point you could. So like if A and B both have a storage variable X, like what is that?
I want to say nowadays you have to actually say override, at least on a public variable. So like on a public, it'll do that. But in terms of internal, like, my God, that sounds like a nightmare.
Well, I want to say that inheritance has been like super successful for Solidity because it's really easy to like import functionality. And that has been like super useful for anybody trying to deploy ERC20 tokens or like just get some code working very quickly. But there's this storage layout issue. There's also a name spacing issue. Like if you want to find out, like if you reference something like this.foo, you have to like look through the entire inheritance tree and reason about it in order to figure out what foo is, whether it's a method or a storage variable. So like, yeah, so you need to do like, you can't just look at a contract and see what storage variables it uses, or like every usage of some storage variable X. I mean, in some ways you have to like have genius levels of working memory in order to reason through inheritance trees, right? Like you have to have like you have to be able to load every single contract into your working memory that you inherit from in order to like figure out what some contract does.
Mm-hmm. Totally. Yeah, I remember like Josh first looking at like Superfluid's code base, right? And we're inheriting from a lot of different contracts. And like, I remember, I mean, it's in Solidity, right? So this is the way it works. But like I had like 4 VS code tabs open, each of them with like multiple like windows, and just looking at it all at once and just tracing it through. So I've totally experienced that. I just wanted to interject and say that.
Yeah, I mean, for sure. I'm sure any Solidity developer can tell you about something similar. So, I mean, the technical way we would say this is that like you need to do semantic analysis on your contract in order to understand how storage variables are being used. And possibly you need to do like static analysis or use heuristics because there's like storage pointers and like you can mess with them with assembly. So there's there's like no static way in general of finding out how specific storage variables are used in a Solidity smart contract or in any smart contract language that has properties similar to Solidity, like inheritance and being able to mess with storage pointers. I think ideally for the smart contract domain, you would want to be able to very easily find out what happens to storage variables because like that's like really important for the behavior of your contract. You want to like maybe without even having a compiler be able to tell like what are all the variables that are used in this contract? What are all the variables that are modified in this contract? Where is foo modified? Stuff like this. And that's like very important for being able to reason about your code. And as just like a point about programming philosophy in general, anything that you can do to minimize your cognitive overhead is like extremely important to program correctness and design and optimization. Like if you think about your brain as like having some like limited working memory, you want to use as little as possible in general so that when you need to, you can use the rest of it. So as much as possible, you want to make your programs as simple as possible so that when you need complexity, you can access it.
You know, one last thing here, you know, on the technical side that, you know, I'm really eager to jump into. I'm really excited about. So tell us a little bit about like what is, you know, Titanoboa and, you know, what's the objective here?
So I think there's two reasons for Titanoboa. One is that historically Vyper has not gotten as much tooling support. So people who are writing and maintaining tools support Solidity first, which is fine. Obviously, it makes sense for them. But, you know, as Vyper people, we want to have feature parity with what you can do in Solidity. We don't want people to be coming in and being like, hey, you can do XYZ in Solidity. Why can't you do this in Vyper? Why can't you do something equivalently powerful in Vyper? So on the tooling side, I think historically we have not had as much support. And that's kind of changed in the last year or two. You know, there's more options. There's Brownie, Hard Hat supports Vyper 2, obviously. The other thing is that what Titanoboa enables is just, in my opinion, frankly, kind of cool. So Banteg was saying to me, wouldn't it be cool if you could like prototype a Python contract and then have it be a Vyper contract? So this idea of being able to prototype and having like kind of a Python kind of experience when you're writing Vyper kind of spurred a lot of the development. I kind of took that and ran with it a little bit. I was like, wait, what if you could like have a Vyper interpreter? So I like started implementing a Vyper interpreter. And like the classic way of implementing an interpreter is like, I mean, this is like textbook, right? Or what you learn in compilers class or something. You like step through every step of the program, and then every step you just like evaluate the semantics or like whatever the language is supposed to do. You know, if X is supposed to increment by 1, then you implement that in the interpreter. So that's what I started doing. I like started implementing the rules for the Vyper language. And then after like a couple days of this, I was like, hang on, this is like this is like redoing all this work that like the Vyper compiler already does. Like we already know how to add numbers. Why am I re-implementing this? I started to take a different approach, which is like we can pretend to be an interpreter. The strategy is like, well, okay, so there's a lot of benefits to having an interpreter. Like you can do all sorts of things that the compiler doesn't necessarily do, or like you don't get in a compiled language. The goals are very different. So like when you compile Vyper code, you want like the smallest binary possible you want it to like run on the EVM, and like a lot of things, a lot of like user-facing things are not as important. But in interpreter, you like have a lot of context about what's going on, and performance is not as important. So you can do things like simulate what happens on like some state, or you can like do tracebacks. So then the question was like, well, how can we like get all this interpreter features without like re-implementing all of this functionality that the compiler already does? And I started to go down this route of like, what if we just like compiled the contract and then like pretended to interpret it? Because like we have an EVM. Like, what if we just like looked at what the EVM did and then like pretend we interpreted it? And so that's what Titanoboa actually does. So, and that's the entire design of Titanoboa. And in some ways, it's very hilarious. It's just like monkey patch the entire thing. Titanoboa is like this generalized execution environment for Vyper. After I got the initial Titanoboa implementation working, which is like it uses PyEVM, which by the way is quite a nice library, I realized that you could like start overriding a lot of PyEVM functionality, and you could start like enriching it with like stuff you would like to know about Vyper. I think one issue people have a lot of issues with when they're developing smart contracts is it's like kind of hard to debug them. You know, like your program reverts or like fails with execution reverted, and you're like, why? So one constraint in the Titanoboa design is that it's like pinned to a specific Vyper version, and that's a trade-off. So like you can't compile Solidity code with Vyper. You can't like compile old versions of Vyper code with Titanoboa. But what that allows you to do is it is able to take a lot of the compiler internals and make really convenient UX. Titanoboa now has like, since I work on both Vyper and Titanoboa, I added these error maps into Vyper. So like a lot of issues are like with compiler generated reverts, like safe math, or like auto reverting on when you like call a contract and the call fails. Vyper now generates reasons, and so like if you have the opcode or the PC where like some transaction failed, you can actually get the reason for why the compiler, like some compiler inserted check and why it failed. And so like now Titanoboa like shows you that. And it also enriches failures with like stack traces. So they're like Python style stack traces. You see, you know, it kind of looks like a Python stack trace when stuff reverts now. So like you can see the entire history or like call stack of like why stuff failed. Also and then once you have this architecture, you can start doing kind of cool things because you're not restricted by an RPC anymore. So the way all these frameworks work, like Hard Hat, Truffle, Brownie, and I was thinking about Foundry, and Foundry is different because it kind of gets around the RPC problem by having a special VM and having these cheat codes and stuff like this, which in some ways is conceptually similar to what Titanoboa is doing. So once you're not restricted by what the RPC allows you to do, you can start instrumenting your execution at a very fine-grained level. So one example is like in Titanoboa, the SHA-3 and SStore opcodes are like overridden. They're like patched. So they like do something that's not exactly what the PyEVM implementation does. And what they do, which is besides what the PyEVM implementation does, is it doesn't mess with the EVM semantics. But what it does in addition to what PyEVM does is it traces them. So like on any execution of a Vyper contract, you can actually enumerate mappings. So like mappings, the keys are like normally erased at runtime, but in Titanoboa, it traces all of them. And so like you can access it as like a Python dictionary. So you can do things like check that the entire like you can do things which like test what the entire contract state is before and after some code executes. So another thing you can do in Titanoboa is like eval arbitrary Vyper code, which is something that you kind of expect an interpreter to be able to do. And the way that works is by like, again, pretending to be an interpreter. It like compiles the code. It actually runs the Vyper compiler. So it actually semantically analyzes and compiles the code using Vyper as a library, and then it runs it using PyEVM. There's also line-by-line gas profiling, which somebody asked me for, a week or so ago, and they're like, it'd be really cool if, we could profile every single line and see where the hotspots are. And so now you can do that with Vyper and Titanoboa, and it'll show you like where the hotspots are, and there's different ways of sorting the profile. Other things you can do with this architecture are like in Foundry, there's like cheats, right? There's ways of interacting with the outside world that are not part of the EVM. And in Titanoboa, you can actually go one step further and like define your own cheats. And you can do this by just like registering a precompile with PyEVM. And with this, you can do like lots of different things. You can interact with the outside world. You can interact with the file system. You can, like, let's say there's some complicated function that you need, like some math function, like natural log, and you don't already have an implementation in Vyper because it's maybe difficult to implement. What you can do is like you can register it as a custom precompile, so it's like not a blocker, and you can like work on other stuff, or like maybe work on stuff in parallel with somebody else until that particular piece is done. And you can, stuff that I end up having to do in order to like implement functionality is like you can kind of modify the virtual machine on a very fine-grained level. So like, let's say for purposes of simulation, you want to like mark storage slots as cold. Again, you can do that. The way I implemented forking, so you can fork mainnet with PyEVM now, or any RPC really. And the way to do that is like just to mess with the specific internals of PyEVM that are related to like getting and setting accounts in storage. And so like it's strictly more powerful than RPC, because anything that you can do in RPC you can do with Titanoboa, but you can also override anything you want in the VM. So like it's really gives the user a lot of power to like modify how stuff is executed.
Mm-hmm. Yeah, Josh and I were talking before this, and I really think more people should follow your work on it on Twitter, right? So we'll let you plug your Twitter handle here in a little bit. But yeah, I mean, I think the community is going to really appreciate this as it continues to get rolled out. So keep up the good work with it.
Yeah, and the other thing is it's an embedded EVM, right? So you don't need to spin up another node to run your tests. So this makes multi-threading work. So like if you want to spin up a million cores, run, some tests over, you can do that, and all of them are running their own EVMs, right? And so because it's all in process, you get fairly easy access to like any Python functionality. So like you can just use PyTest, and that like gives you a lot of functionality right there. Like there's PyTest xdist, which is like parallelizes your tests automatically. There's like PyTest hypothesis, which is like a very general fuzzer, and you can do like fairly complicated things with it too, like different strategies, which maybe we could expose more cleanly in Titanoboa, but you can implement something very similar to Foundry's assertion invariant testing. Like I said, you can do anything in Python with it. So like in order to like configure your tests, you can like run arbitrary Python code before like you enter the Titanoboa execution. Or you can like using user-defined precompiles, you can actually like have two-way bindings between Vyper and Python. So you can like interrupt your test or interrupt your Vyper code, do something in Python, and then come back.
Sweet, man. Yeah. So before I ask the final question here, I know you have to run here in a bit, so I won't take up too much more of your time. Where can people find you on Twitter? What's the handle?
It's big _tech _sucks SUX.
And where'd that acronym, or not acronym, where did that come from? Is it just like the first thing you picked that was funny, or did you have a particularly bad experience with big tech that made you pick that?
I think I was just like spitballing with some friends, and they're like, "Big Tech Sucks," and I was like, "Yeah, that's it." And my background photo on Twitter is that is that go to fail bug. Where I don't know if you're familiar with it, but it's in an SSL implementation, and it was probably introduced by some strange merge. But basically, the bug is it's some switch case statement or like an if statement, and then there's no brackets because it's C, and so it's like if condition go to fail. So, and because of the indentation, it looks like it only executes when the condition is there, but it actually always executes.
That's so good. I love it.
And maybe that's like a little bit cranky of me, but I feel like that's what happens at big tech companies with too much bureaucracy.
I love it. Yeah, I love the Easter egg shot at big tech in the header. That's fantastic. Okay, so final question. This is more broad, and you can take this wherever you want, right? But let's say we fast forward 5-10 years and we look at where crypto is, right? In 2027 or 2032. What do you hope that we accomplish by then? You can answer this from the micro, as in like, I want Vyper to be able to do X, or it can be macro, as in like, hey, I want the world to look like Y, right? Feel free to take that wherever you want, but I'd love to hear your answer.
That's a really interesting question, and I'm sure a lot of us think about that a lot. Some people, and I see this vision of the future a lot, and some people think in 10 years, crypto is going to be used everywhere. Just regular people won't know it. It's going to be used on the back end by like JP Morgan and, Bank of America or whatever, or the stock exchanges. And I think if that happens, then crypto really isn't living up to its potential. I don't see everybody and their dog or whatever using MetaMask or like, the kinds of tools that people use today, because the UX is very niche still. But I do hope that people in general are accessing crypto directly. And I think it's kind of important for people to do that, just in the same way as like people use encrypted messaging apps now, because people can understand, even your regular person can understand that their privacy is important. In the same way, I really hope that people understand that self-sovereign access to money is important, even if they don't necessarily have to use it on a daily basis. I really hope it doesn't get stuck behind, a walled garden or something, where like these quote unquote institutions are using it on their backend. I really hope that the nature of financial institutions change as people kind of more have better tools and in some ways can become their own financial institutions. And I think that DeFi, and if I can even talk about this, Tornado Cash, are like really good examples of this. I was talking to my non-crypto friend about Tornado Cash, and they were like, "What's that?" And I was like, well, it allows you to have privacy on the blockchain with your like financial transactions. And they're like, oh, so like money laundering. And no, I hope that people can understand that just because you use this, it doesn't mean you're a terrorist, in the same way that if you use Signal, you're not a terrorist. I'm also really happy with how DeFi has turned out. I was thinking about this. Vitalik Buterin tweeted recently, like, how sending money internationally is like a worse experience than using cryptocurrency. Sorry, I shouldn't say sending money via bank internationally. And I think the experience of using crypto right now is like, let's face it, it's not great, but at least it's like as bad as it gets. Like if you use a third party, like a bank or something, it can get like arbitrarily bad. Like you can have one experience one day and a different experience the next day. And like with cryptocurrency, it's like only up from here. And there's like a consistency to the experience too. And like you can use DeFi. You can like now you can like actually be your own bank and you can have access to your own investment products. And yes, it's like a little weird. Yes, there's like a lot of bugs and like scammy projects out there, but you do have that ability to do things yourself. Not everybody has to do that. Not everybody, you know, goes to the grocery store and by themselves. Like a lot of people use DoorDash these days. Not everybody uses Signal or WhatsApp or like encrypted messaging apps. But a lot of people do. And I think it's important for people to understand that not only can they do that, but there's enough of an industry to support them that it's practical.
Yeah, it's a fantastic answer. And I think our listeners will agree with a lot of that. So thank you again for coming on. Again, it's at Big Tech Sux on Twitter, big_tech_sucks. I'll be sure to link all that in our show notes. Josh also compiled a list of like threads and tweets you've done on some of the awesome new things you're building into Titanoboa. So we'll be sure to link those as well. And guys, if you're listening to this and you're curious about Vyper, or if you're maybe a Python dev and you're just more familiar with like Pythonic syntax and things, go check out what Big Tech Sux is doing with Titanoboa. I think you're going to really like it. I think it has a great potential to be an amazing developer experience for this space. And I'm excited to see where it goes.
And also, if you want to use Vyper, try out Vyper or Titanoboa, feel free to hop in our Discord. I try to, me and other Vyper folks try to be extremely responsive. To the point that if people are like, why can't you do this in Titanoboa? We implement it. So we're very responsive to feedback. We like getting feedback because it helps us make everything better. So you're welcome to hop in there.
Wonderful. Well, thanks again.
Thank you for having me. This has been really enjoyable to chat with you guys.